Hello, Physics 20s. Welcome back. We are on Unit 4, Lesson 2. We're talking about energy. In particular, we're talking about kinetic energy as our focus for today. And you might be thinking to yourself, I already know everything there is to know about kinetic energy. We looked at that in Unit or in Science 10. Probably not the case. We're going to explore it a little bit more here in Physics 20. So first and foremost, a little bit of review of what we talked about last time. We said that work is a change in energy. Anytime we're doing work, we're changing the energy, or at least attempting to change the energy of an object. So what types of energy are we thinking about? So obviously this person right here is doing work on the person holding the video camera. They're doing some extreme shots, gonna maybe put them on YouTube or something. But so the person's doing work on the other person. It looks like in this case they're going to increase their speed if they're sitting on a skateboard. And if they increase their speed, we know that they're increasing their kinetic energy. This person over here is lifting a box, right? And if they're lifting the box, it's going from a height down here to a height up here. They're doing work on the box. They're applying a force. It's moving a distance, and the box is changing in height. You might remember from Science 10, well, a change in height, that corresponds to a change in gravitational potential energy. Perfect. So, what we're looking at for our Physics 20 here is three types of mechanical energy. So we got kinetic energy, and it's really good to know when you have these types of energy. So kinetic energy, that's when we have speed. Anytime something's got mass and speed, we've got kinetic energy. Gravitational potential energy, anytime a mass has height, it's got gravitational potential energy. And then finally, elastic potential energy. Anytime something has been stretched or compressed and it wants to get back to its original shape, we've got spring potential energy or elastic potential energy. Often those two terms are used interchangeably. Cool. Something that's really important to note is no matter what type of energy we have, they're all scalars. So again, think to yourself what exactly a scalar is. Well, that is magnitude only, no direction. So we got the ones that we're going to talk about: kinetic, potential, maybe a bit of spring here and there. We've also got heat energy, nuclear energy, electrical energy, and so many other types of energy. All scalars. Never, never, never do they ever have direction. Cool. So again, our focus for today is kinetic energy. That's energy, again, due to speed or due to motion. So you might think this person is a runner, and obviously runners have speed and he's got mass, but no. Rollerblades, getting ready for spring here. Cool. So one question that you can think about: how do you know something has energy? And it always comes back to work is equal to a change in energy, or a change in energy is equal to work in this case. So could the car, if it's moving, and if it moves and it smashes into this block, could it do work on the block? And if the answer is yes, if it can do work on the block, it can apply a force and it can move a distance, it's got energy. That's an easy way to tell if it's got energy. Perfect. So again, if it can do work on something else, so if the car can change its energy and do work, or change the energy of something else, perfect. We have got energy. Now, our formula or our equation for kinetic energy, you've seen this one before. Kinetic energy is equal to 1/2 times the mass times the speed squared. And we're being very specific to say it is the speed in this case, not the velocity. And we use our standard units. So mass, if we're in physics, we're definitely using kilograms, speed, meters per second. And our energy for this is, in fact, joules. Perfect. Perfect. Just like work. Work is also measured in joules, just like any other type of energy measured in joules. Perfect. Now, one thing that we're going to have to get more and more and more used to, and is actually quite big in Physics 30, is figuring out alternative or equivalent units. So an equivalent unit for a joule, well, I can go through and I'm going to start with my original formula. EK is equal to, and you know how I actually like to write it? I like to write 0.5 mv squared. That being said, multiplying by 0.5 is the same thing as multiplying by 1/2, is the same thing as dividing by 2. So some people even take that and they go mv squared over 2. It's all the same thing, right? Cool. So things that I like to do, I say, okay, well, kinetic energy is a joule, and all I'm really doing is replacing the units that I've got in my equation. Kinetic energy is measured in joules. The 0.5 doesn't have any units. It's just a 0.5, so we're going to leave it there. The mass is measured in kilograms. Perfect. And then the speed, well, that's meters per second, but that meters per second is going to be squared. So we could write it like this, but then we can also expand on that. So a joule is a kilogram times a meter squared over a second squared. Joule is the same thing as a kilogram meter squared over second squared. Cool. So we know an alternative unit for that. So if we're using this formula, here's a little challenge for you. If we're using this formula to figure out that a joule is equal to a kilogram meters per second squared, shouldn't this formula, do it in a different color maybe, work is equal to force times distance? Could you, one, figure out an alternative unit for joules from this one? And then two, could you try and go through and figure out how a joule is going to be equal to a kilogram meters squared over second squared? Because that's a little bit trickier. Put the video on pause. You can try it out right now. Go for it. Okay, so what you may have gotten to is work is equal to force times distance. I don't know why I'm writing out the exact same thing again. We may have said, okay, well, work, that's measured in joules. Force, that's measured in newtons, and distance, that's measured in meters. So you've already found another unit for joules. Joules could be measured in newtons times meters. That doesn't necessarily help us out getting into kilograms meters squared over second squared, but that is an alternative unit. So let's try this one more time. Let's say work is equal to force times distance. I'm going to put that as the net work based on the net force, and then maybe things will become a little bit more clear. So joule is equal to a force. So force is mass times acceleration. Real easy to see when you're using the net force. Excuse me. And then d is obviously distance. So now when I go through, I'm getting ahead of myself a little bit there. Should still be formula, not units yet. So then when I go through, I can start to plug in the units. So work is measured in joules. Mass is measured in kilograms. Acceleration is meters per second squared. And then distance is measured again in meters. Perfect. So when we simplify this, it's a lot easier to see. I'm just going to clean it up a little bit here. Meters times meters, well, that's realistically meters squared, and all of a sudden we're back at the same place. Any single time that you rearrange and you try and figure out what a joule is, it should always work out to be kilograms times meters squared over second squared. Cool. So moving on a little bit here. Another important thing to note is that kinetic energy is always positive. We saw in the last lesson where work can sometimes be negative if it's trying to take energy out of the system, or it's opposite to the motion. If the force is opposite to the motion, it's negative work. We'll see that gravitational potential energy could again be negative. But again, negative does not mean a particular direction. It just means more or less than taking energy out or putting energy in. So kinetic energy, though, always positive. Don't even worry about it. Never, ever, ever put a negative with kinetic energy. Cool, so let's jump into an example already. So we got an object traveling at 45 kilometers per hour and has a kinetic energy of 120 kilojoules. All right, so let's start to highlight some things here. This is my speed. It's got a kinetic energy of 120 kilojoules, tells me right in the question. First part is determine the mass. So mass is my question mark. Anybody notice anything funky about this question right off the bat? Those units, hey? Kilometers per hour and kilojoules. We don't really want that. So EK, let's change that into 120,000 joules. And then 45 kilometers per hour. If you're using the shortcut, just know, because remember the magic number for kilometers per hour to meters per second is 3.6. Just know when you're multiplying and when you're dividing. If you're using conversion factors, it's a little bit easier. This one, when you plug it in, should be 12.5 meters per second. Cool, I think we're ready to solve for part A now. So for part A, let's go through and let's start with our original formula. EK is equal to, I'm going to use 0.5. I really like using 0.5 for things later in the course, but if you're using 1/2, that's okay. 0.5 mv squared. Cool, so now I'm looking for my mass, so I have to rearrange. So I'm multiplying by 0.5 and multiplying by v squared. So let's divide both sides by 0.5 and divide both sides by v squared. Don't know why I did that off to the side, a little funky. So 0.5 cancels, v squared cancels, and we are left with mass is equal to ek over 0.5 v squared. Now, if you were using 1/2, you might end up with, I'll just do this off to the side way over here, you might end up with mass is equal to 2 ek over v squared. That's okay. Or you might end up with, if you're really using the 1/2, you might end up with ek divided by 1/2 v squared. But again, I don't really like fractions inside of fractions, so you can keep change flip and go to put the 2 on top. Either way you look at it, it's all going to work out to be the same thing though. So I'm going to erase these and stick with the one thing that we've got over here. Okay, so plug in numbers, that's 120,000 joules divided by 0.5 and then also divided by v squared, so 12.5 meters per second, and then squared. You'll notice that I put the squared outside of the brackets to make sure we're doing that too. Not just the number, but the unit as well. Like everything inside of brackets is being squared. We're not confusing it with an acceleration or anything like that. And then we go ahead in and we plug in some numbers. So maybe put your video on pause and plug in these numbers, see what you get. So I got 1,536 kilograms. It's a pretty big object, but that being said, maybe it's a car, right? And that's sort of a truck, and that works out a-okay. If you didn't get 1,536, you know what a really common mistake is for this? Just forgetting to square or square root. We're not really square rooting in this case, but forgetting to square. Now, one thing to kind of look at with this, is this okay for a final answer, 1,536? Not really, right? It doesn't take into account significant digits. So I'm going to put it as 1.54 times 10 to the power of 3 kilograms. And that's what I want to put a box around and say, hey, that's my final answer. Cool, so there's part A. Let's check out part B real quick here. Okay, it then loses 70 kilojoules of kinetic energy. Loses 70 kilojoules of kinetic energy. Determine its final speed. So there's a couple different ways that we could look at this one. Part B. And probably the easiest way to go through and look at it is say, okay, well, if it's losing energy, that means its energy is changing. So its change in energy is equal to, and change in anything, I hope you remember, is final minus initial. So this is going to be EKF minus EKI. Perfect. Now my change in energy, that's where it's losing 70 kilojoules. All right, so use this as a slightly different color up here to make it stand out. My change in energy is going to be equal to negative 70,000 joules. And the reason that the negative is in there is because we are losing that. So it should be less when all is said and done. Cool, and then we started off with 120,000 joules. So you could probably from this figure out how to get EKF. So let's see, EKF, our final kinetic energy, is going to be equal to my change in energy plus my initial kinetic energy. So all I really did was take that kinetic energy and add it to both sides of the equation to get EKF all by itself. So now I've got negative 70,000 joules plus my initial kinetic energy, which was 120,000 joules, and we add negative 70 to 120,000 joules. Take a second, plug it into your calculator. So negative 70,000 plus 120,000. We should end up with, yeah, that makes sense, 50,000 joules. Probably didn't need a calculator for that one even. So positive 50,000 50,000 joules. And then we can even think to ourselves, does this make sense? So if I'm starting with 120,000 and then I lose 70,000, makes sense that I end up with 50,000 joules. Perfect. So last thing that I really want to look at here, I'm just going to have a line to kind of separate this. Separate it nicely that way. Last thing that I really want to look at from this is, well, I've got my final kinetic energy, so EKF is equal to 0.5 times the mass. Hey, we figured out the mass up here, so that's convenient, times my final velocity squared. I am now looking for my final velocity, so as I rearrange, I have to think to myself, reverse order of operations. So let's see, I will have to eventually get rid of the square, but first, I have to get rid of the 0.5 and the m. So 0.5 and m, let's divide both sides by 0.5 and m. So those cancel, and now I'm left with v squared is equal to EKF divided by 0.5 m. Cool. Only thing that's really left here is to get rid of this square, and the opposite of squaring is square root. So we will just take the square root of both sides, and that is horribly, horribly, horribly messy. So I'm going to rewrite this one last time before we start plugging in numbers. So VF is equal to the square root of EK over 0.5 m. So let's plug in some numbers. We got 50,000 joules divided by 0.5 and also divided by 1,536. And we want to make sure we're not using the rounded answer for this one, but the whole entire mass. And of course, that's in kilograms. And then, again, that common mistake, forgetting to square and square root things. So just do not forget to square and square root. Take a moment, put the video on pause, plug things in, and see what you get. So I ended up with 8.0, let's see, with rounding, 7 meters per second, and I hope you ended up with the same thing. If you didn't, again, double check that, forgot a close bracket there, that you square root things, double check that your rearranging is correct, and double check that you're typing things into your calculator correctly. Cool. So there's our first look at one of those. Bit of space for me to work, bit more space for me to work. Let's just check out one more example. This one's got a bit of a definition-y stuff, so things that we have talked about in previous units and even in previous lessons. So let's jump right in. We got an 8,000 Newton car. And you might be thinking to yourself, okay, 8,000 Newtons, you recognize that before, or from before. That is actually our force of gravity, right? So our force of gravity on the car, or the weight of the car, is 8,000 newtons. So it accelerates from rest to a speed of 15 meters per second. So from rest, that's going to be VI, to a speed of 15 meters per second, that's going to be VF, along a level surface. Okay, cool. The work done by the propulsive force is 110 kilojoules. So that's my work being done, and we might as well change that into regular plain old joules. So 110,000 joules. Determine the work done by friction. Cool, so the work done, and you know what we might even do with this? Let's make that a little bit more specific. Rather than just saying the work done, let's say the work done by the applied force is equal to 110,000 joules. Cool, all right, so a bit of a bigger question here. You might want to put the video on pause and just think about a bit of a plan for this one. So how can you relate the work done, the net work done, because we've got more than one work being done here. How can you relate the net work being done to the change in speed and the change in kinetic energy? Again, put your video on pause and maybe see if you can come up with a plan. So if you're thinking along the lines of the work is equal to a change in energy, you are absolutely spot on. One thing that we want to add to this, though, this is the overall work is equal to the overall change in energy. So I'm just going to add the net work is equal to my change in kinetic energy, because that's sort of what we're looking at here. Net work is equal to our change in energy. So if I'm looking for my net work, right, I'm trying to figure out my net work, well, remember from last lesson, net work is just the sum of all the work. So that's my applied force plus my work done by the force of friction, which I don't think I labeled up here. Work done by force of friction. There we go. And then my change in kinetic energy, well, that's just change in anything. Well, it's EKF, so final minus initial, EKI. So all of a sudden, this doesn't look quite as daunting. So just kind of thinking our way through with this, if it starts from rest, do I have any initial kinetic energy? If it starts from rest, 0.5 mv squared, the whole thing is just equal to 0. So we can kind of cross that one off right off the bat. Now I'm looking for my work done by force of friction. I'm adding my work done by the applied force to it. Cool. So all I'd really need to do to get work done by force of friction is subtract the work done by my applied force from both sides. So that's going to get rid of that one. Cool. I'm a little bit messy here again. Rearranging can turn into a bit of a mess. So I'm just going to rewrite this. Don't need that part. Just going to rewrite this. Work done by the force of friction is equal to my final kinetic energy minus the work done by my applied force. Cool. All right. I think we're almost there. Almost there. We might run into a bit of a roadblock here. I bet you some of you probably already figured out what that roadblock is. But EKF, that's 0.5 times the mass times the final speed squared minus the work done by the applied force, which the question just tells us, right? I better double check that, I suppose. Yeah, the question just tells us, so we can go ahead and just rewrite that one. Okay, cool. We're ready to plug in numbers. Or are we? What's missing from this? We know what 0.5 is, duh. The mass, we don't have the mass yet. I think everything else we've got. So let's go back up to the question and let's see if we can figure out what the mass is. So an 8,000 Newton car, and then nothing else that would have anything to do with mass. So that 8,000 newtons, that's my force of gravity. How can we get force of gravity? How can we use that to figure out mass? So I'm just going to do this off to the side over here. As a little bit of a side note, the force of gravity is equal to 8,000 newtons, and we know that force gravity is equal to mass times gravity. Ah, there it is, right there. So mass must be equal to Fg over g. So that's going to be 8,000 newtons over 9.81. I'm going to use newtons per kilogram on this one rather than meters per second squared, because look what happens. Beautiful. The only thing we're left with is kilograms. So let's plug that into our calculators. 8,000 divided by 9.81. What did you get? You got 815 kilograms. I think you're doing all right. Absolutely all right. Now, of course, it's 815.49, blah, 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 blah. But for now, we'll kind of leave it as that. We'll just won't round until the very, very end. Okay, I think we're ready to plug in some numbers then. So 0.5 times 815.49 kilograms times the final speed squared, which I believe was, yes, 15 meters per second. 15 meters per second, but of course we want to square that, and then minus our work done by the applied force, so that's 110,000 joules. So again, take a moment, you can put the video on pause if you'd like, and plug the numbers in, see what you get. So I ended up with negative 18,257, that's not a 7, 57 joules, which doesn't really have the correct sig dig, so I'll write that out one more time. That is negative 1.83 times 10 to the power of 4 joules. That's what I want to put the circle or the box around. That is the work done by my force of friction. Now we got a negative number. Does that make sense? Think back to Unit 3. Well, and the first lesson realistically. So I got a negative number. That means that my force must be the opposite direction to the distance, right, or to the motion, which makes sense for friction, right, because force is always opposite to the motion. And that means that this work must be trying to take energy out of the system or slow it down, which also makes sense because that's what friction does. Nice, perfect. So I think we've got it here. Now it's just on you to do a bit of practice and make sure you know what you're talking about. So that is it for now, Physics 20s. I will see you again when we talk about gravitational potential energy. See you later.